Yes, it's 5 p.m. Ladies and gentlemen, I'm quite happy to introduce our speaker of today. It's Professor Schahram Dustdar from TU Wien. Schahram is really well known for his work in cloud computing, distributed systems, and more he looks at, I would say, the so-called non-functional requirements, which are perhaps getting functional requirements in the sense of, sustainable systems, intelligent systems, as we see here. So we are really very much looking forward and are happy to have you here, Schahram, and it's your floor.
Thank you very much, Gerti, for the nice introduction. As we just discussed, I will also switch off my video to save bandwidth and energy. All right, so as you know, distributed systems are really key to our society. So all the underlying infrastructures which are critical nowadays with applications such as smart cities, healthcare, autonomous vehicles, etc., they are really distributed systems. And they constitute the interconnectedness or the fabric, if you like, of the components, being hardware, software, but also people, bringing complexity. And that you can see here in this picture, spanning everything from the IoT domain via the edge domain, the fog and the cloud, and of course also be distributed all over the place. So around 20 years ago, we basically have seen the emergence of cloud computing, the cloud domain, as you see here on the right-hand side. And pretty much everything was focused on the cloud domain in the last 15 to 20 years, till now also. But more and more, we see the compute continuum being composed of different parts or tiers of the infrastructure, spanning from the left-hand side, the IoT sensors, the edge domain with low reliability, highly volatile systems, highly mobile, small form factor, energy constraints, typically controlled by end users or service providers. Moving to the right, we can see the traditional, so to speak, edge computing. These are typically computers with different capacities regarding compute and persistence, etc. But nevertheless, they are at the edges of the networks. This means that they have a lower latency to the end device. And they are typically general purpose computers of different shapes and forms. Sometimes they are controlled by telcos, sometimes they're also controlled by companies. And as we move to the right, we can have the fog domain with a core network with base stations, for example, typically controlled by the telcos, which in principle, not realized fully today, but in principle could be, let's say, higher powered edge computing infrastructures. And on the right-hand side, the cloud domain, which is typically what we have today with the unlimited compute and storage resources, the full spectrum of cloud services with high availability, low cost providers typically. Now, what I am basing my research on is to look at this whole compute continuum as the new infrastructure. So not only the cloud, but also think about which parts of any applications can be deployed on the fog, deployed on the edge, and deployed on the edges of the overall infrastructure, namely, so the compute continuum. And this brings with it a number of very interesting problems to solve, namely also in the energy and sustainability domain. So all of these different applications, like the autonomous vehicles, health, industry 4, virtual reality, augmented reality, but also the question of resources, etc., they really are based on the problem of distribution and decentralization. And we can save a lot of energy if we actually provide the infrastructure where these applications are being deployed at in a clever way, in an intelligent way. As you know, increasingly, intelligence or AI is becoming more and more important. So the compute demand is also growing. This means that we have these large transformer models which require a lot of energy when we train them. So training, for example, ChatGPT requires a lot of money, a lot of energy, and running these ChatGPT infrastructures, as you can see here, also requires a lot of money and a lot of energy as well. So the question is, can we actually save energy? Can we save money and be also good for the planet as well? So the question then becomes, can we build sustainable distributed compute continuum system where we are aware of the energy consumption on different levels of abstraction regarding the origin, regarding the usage, regarding the forecasting? And this brings a multitude of problems, of course, because most of the current research is currently on energy efficiency. But giving specific usages, also we require new algorithms to reduce the recorded consumption as we need it. And this energy awareness is very hard to obtain for us nowadays. And I would like to bring the analogy to the human body, which is kind of interesting, because it's also a complex system similar to what we are dealing with here in this compute continuum. The human body is comprised of a series of complex systems. So for example, we have the skeletal system, we have the nervous system, we have the cardiovascular system, and they constitute an infrastructure. But we also have the lymphatic system, we have the endocrine system, which determine the regulation system of the body. And if you look at the infrastructure part, the nervous system, with the brain as its main component, it has a highly sophisticated compute infrastructure, as we are all aware of, right? So it has 86 billion neurons, and these 86 billion neurons have a high computational power, even though they run just with 20 watts of energy. But we have more. The cardiovascular system also is a compute infrastructure. So with 40,000 neurons, it also helps the body to meet the demands. So typically, if you're not aware of it, the brain is often compared to the cloud. It is a centralized system. But for example, in the body, which is a system, not all the decisions are done in the brain. So the autonomic nervous system, which the heart is an important part of, is completely responsible for determining also the heartbeats. So it's not like the brain is doing that, it's determining that. So we have different computational centers. In fact, we even have the gut with around 100 million neurons as well. So we have in the body 3 computational systems, centers, if you like, which are messaging together with the proteins and all the messaging infrastructure that we have, and exchanging events, exchanging information about how to optimize the overall infrastructure that we have. So I will take this as an analogy for us, what we want to build by taking these different parts of like the human body. We would like to map that to the compute continuum. So we would like to use the edge computing infrastructure, the fog computing, and the cloud computing as well. And so we're looking for inspiration in nature, if you like, in the human body. If we go more with this analogy, we also have regulation systems, such as the lymphatic system, which is part of the immune system protecting our body against foreign invaders, right? But of course, the analogy is just an analogy, so we should not get too much caught up. But what we can learn from looking at the infrastructure of the human body is that we need to find out the right abstractions. How can we model these infrastructures? And this is what I'm going to talk about today. So this is the concept of deep SLOs, as I will explain to you in a minute. But there are also other parts regarding learning and regarding zero trust, which are equally important, but which I don't talk about in this presentation. So the core of my approach of achieving sustainability in this distributed compute continuum is to create an intelligent infrastructure which provides necessary tools to handle this energy efficiency. And we do that by creating a hierarchically structured set of service level objectives. The service level objectives is a concept which we know very well from cloud computing, which is essentially a set of relationships between metrics. And this is something that we are able to determine the functions, the non-functional properties, as Gertie mentioned at the beginning of her introduction. And we create these SLOs in an approach to build these systems, to specify these systems, and we term them deep SLOs simply because they are hierarchically structured. So whenever something is hierarchically structured, typically you can use the name deep. So here you can see an example of metrics, which are the gray boxes, and SLOs, which are the green boxes. So for example, the SLO with a total CO2 emitted amount is depending on metrics, right? So different metrics go into this SLO. So we have to measure the energy source, we have to measure the power consumption in this example. So this constitutes the SLO. Whenever this SLO is defined and the requirements are not met, we have to define an elasticity strategy. So for example, this means what do we have to do in order to change the balance of these different components of the SLOs? So this is the idea. And then basically what we can do is we can define these SLOs, we can utilize these metrics. So basically, how do we measure them? And structure them hierarchically so that we do have different levels of abstraction as we go along. And each SLO then follows a MAPE-K loop, as you know that from autonomic systems, with monitor, analyze, plan, and execute, and is able to access the policies from a lower SLO. And by this, we can obtain loosely coupled interactions between these SLOs, managing the overall system. This is the fundamental idea, what we propose to achieve a intelligent infrastructure, which is our goal. Right? So we want to create this intelligent infrastructure so that the infrastructure itself has the necessary ingredients because it knows the modeling of the SLOs, how to actually deploy its components on the different parts of the compute continuum. So some parts should go on the edge, some parts should go on the fog, and some parts go on the cloud infrastructure. Question is that enough? Does it help us to keep a continuous increase of the computational requirements in our society? Can we develop systems with a fixed computational budget, for example? This is also an important part because in the last 20 years, we have not really paid attention to the computational cost. With the cloud computing metaphor, basically, we just put everything on the cloud regardless of the computational cost, more or less. Now, this is going to change. So the question becomes, how are we able to have a computational budget to fix that, maybe as an SLO, and then keep the infrastructure topology as such so that it adapts to the necessary parts? Now, again, if we look at the way that the human body does that, it does that with the homeostasis principle. So how does the body keep its equilibrium? Homeostasis is just the medical term for keeping a balance, keeping the equilibrium. So typically, if you look at the body, it self-regulates. It does that with temperature, for example, or with blood pressure. So the body self-heals. It learns how to maintain the requirements that the body actually has. So the overall state then goes from top to bottom sensing. So basically, we as humans, we are not able to do deep packet inspection, as I call it, in our own body. So what I mean is that we don't know really what is going on in our kidney, in our liver, etc. We are only able to feel on the high level of abstraction, right? So we are only able to say, okay, we have fever, we have a high blood pressure, but we are not able to say something about the deeper level. And this is problematic for the body, of course, but for the systems, for the infrastructure systems that we create, this is quite different. We can create infrastructures which do have the built-in technologies to create this resilience mechanisms. So how we can do that is we can look into a elasticity metric. So elasticity is a property that we know from physics or material science. We say something about the state of the material following some deformation. So in other words, if we put pressure on a material, it deforms, and if we take it away, the stress, it goes back to its initial. This is something that we have typically done in the past 15 years or so, where we build resilient systems. And the way that we do that is that we just don't look only at scalability, which would be the resource elasticity dimension, but we look at two other dimensions as well. We look at the quality elasticity. Quality elasticity is all the non-functional properties such as performance, the quality of the data input and output, etc., and also the cost elasticity at the same time. So this means that we have a three-dimensional space where we try to optimize the elasticity space of our application. So we look at all the three dimensions at the same time. So for example, we say we want to use these resources, but only if the quality is given as such, and also it doesn't cost more than X. So just to give you an example, we created a language some 10 years ago for the cloud, but we are now shifting it also to the edge, where we are able to specify constraints, like you see here, and attach those constraints to different levels of abstraction, like on the cloud service level you can see here, or on the service unit level, or even to the code which we have directly in the programming language. We can say, okay, define a constraint about data accuracy and the cost. I want fresh data, but only if the cost is not more than X amount of euro, for example. And then we let the infrastructure adapt itself so that it can fulfill the necessary requirements that we have specified for elasticity. So this means that our main perspective, or our main focus of the elasticity requirement of the application is in this three-dimensional space of resource quality and cost. And we are able to say something about the elasticity space over time. So how does the service evolve over time regarding this? And we can also say something about a particular pathway function, which we can characterize a particular elasticity behavior from a particular view. For example, we can look at how the quality is actually developing over the time axis. So this is one important ingredient of our approach. So this means that at a high level state, we look at resources, quality, and costs. And what we want to do is we want to achieve equilibrium, so that this is the underlying assumption, the underlying philosophy where we want to achieve the equilibrium of the overall system. This is extremely important because this is the requirement that we have specified, and we have attached it to the different components of the overall system. So we would like to avoid that the system goes out of balance, right? The way that we do that, as I have indicated before, is we use service level objectives. And these service level objectives represent basically these thresholds in this Cartesian space, this three-dimensional space, which is then delimited within this hexahedron, within this box, as you can see here. So all the infrastructure characteristics, these points, represent the infrastructure, and all the value configurations are inside this hexahedron, and they can be represented by a blanket, a stretch blanket over these infrastructure points. So in other words, all the different configuration possibilities are inside this gray blanket, as you can see here on the screen. So the way we do it is actually we look at a construct, a mathematical construct called Markov blankets. So the Markov blankets are a mathematical construct which says something about the conditional independence to a central variable, in this case the node n, and they only look at the different variables which are determining the value of n. So the parents, the siblings, for example, represented here. And they blend out all the other different nodes, which is quite comfortable for us because this reduces the space of computation that we need to do. So the Markov blanket allows us to separate a thing that we are interested in manipulating from all the environment, all the conditional independence, basically. But it allows us to connect also to other sensory nodes or action nodes. So this means that we are able to say something about a causal relationship. This is the underlying intention of what we do. So the Markov blankets are then able to help us for coarse-grained granularity, so like central nodes, but also for fine-grained granularity, the same principle. Even a single SLO can be influenced by a subset of metrics of that infrastructure. We just need to be able to define it before. So what we want to do is we want to define causal relationships of the application components by using SLOs, and these SLOs then require us to define these different relationships between metrics and the SLOs that we define. And by doing that, we use a causality filter to focus the most important relevant autonomic components. And since we have then a causal relationship of the different parts of the overall system, we are able to make much better decisions about the different topologies of the infrastructure. So we are not just looking at data as a flat thing, but we are looking at a very rich set of SLOs, of causal relationships of these SLOs with the metrics, and we are able then to adjust the different deployments as we want to as we have specified them to meet the SLOs that we have intended to. Of course, the bigger picture then involves also some learning. Right? So we have the infrastructure, we have all these causal relationships on the one hand side. We have a set of metrics where we determine and read what is going on in the current system in real time. We are observing the resources, the quality and cost, and we also have a set of actions where we put infrastructure changes. We have a set of actions which change the environment again. What this means is that we have a learning infrastructure which basically, when we look at the temporal dimension, is that it is constantly changing. So over time, the configuration space from T to T1 is changing. So all these actions that we perform also change the infrastructure itself as well. So this was a kind of an attempt to provide you a theoretical background of how we do it. Very practically, in case you are interested in this, we have implemented this SLO management within a project which we do with, or did with FutureWay in Silicon Valley in the US, called Polaris. And we have open sourced it since January 21. It's run now by the Linux Foundation. You can have a look at this GitHub link, where the key concept is what I've just explained to you with SLO controllers. Now they are focused on Kubernetes controllers, but in fact, they are not limited to that. We are able to specify the custom SLOs based on TypeScript. We are able to monitor the SLOs. We can have predictive models for LSTM enabling SLOs. We can monitor the resources, and we can also enforce the SLOs during runtime with these elasticity control strategies I was telling you before. So if you're interested in the practicalities, I would encourage you to look at this. So on a very high level overview, we are able to monitor everything that is going on in the infrastructure. We are able to specify the SLOs with the modern TypeScript-based language that we have created. And we are also able to control the elasticity strategies as we go along in this overall infrastructure. And on my homepage, or you can find all the publications necessary which follow the GitHub model of the code I was introducing to you before. So from a research perspective, we look at Markovian models. So this is the Markov blanket I was talking about before, which is based on directed acyclic graphs. We look at deep neural networks, and we look at active inference more recently, where all these different models can help us to create relationships, abstractions, and causal relationships between these different parts. And this is a very fundamental and also difficult problem to solve, because if you look carefully, you will notice that the internet itself is not based on any causal relationship of the application. So what we see is infrastructure which is basically purely based on a packet infrastructure, so to speak. And we have applications, which typically software engineering is concerned with. But actually, the infrastructure itself is not aware of the causal relationships of the code of the application that is being executed on itself. We are trying to change that. What we have worked on is a research roadmap where we look into the different parts. So the first part was let's say, the more scientifically oriented concepts that we require in order to achieve this. And this part now is more looking at the practical aspects of the AI components, if you like. So we look at this research roadmap from a quality of experience perspective. So this means is what is the end user actually perceiving? So the end user is perceiving 5 different criteria: the performance, meaning the ratio of computational offloading on these different parts of these infrastructure devices. Second, the cost, so meaning computation, communication, energy consumption cost. Then privacy and security, meaning that it's aggregating local machine models from these distributed edge devices is an important aspect of why actually we also want to do edge computing, because it brings a lot of benefits for privacy. Fourth aspect is efficiency. So we say, okay, we want to have excellent performance with low overhead. For example, when we apply model compression or conditional computation. And finally, reliability, which basically relates to the model upload and download in the wireless network congestion. These are the 5 things that the end users experience, and we map those on 2 parts of research in our research roadmap, where we look at AI for the edge and AI on the edge. And they are quite distinct. So in AI for the edge, we look at 3 major things which are dealing with the topology. So for example, all the questions of orchestration, coordination with the base stations, for example. Second, we deal with lightweight service frameworks for all these quality-aware services. And thirdly, we deal with the services themselves, so computational offloading, user profile migration, etc. These are the aspects where AI for the edge is helping. There are grand challenges in this area. So the question of model establishment. So how do we actually restrain the optimization model? The state of the art is stochastic gradient descent. But the question is, are there other better suitable models? So we are basically just at the beginning, I would say. Second is the algorithm development, meaning that the question of which edge devices should actually be responsible for deployment and execution in such an online manner. And this is, of course, a combinatorial and NP hard optimization problem. And the trade-off between quality and efficiency, where we consider all of these resource constraint devices that I was talking about on the edge, right? So they can come with all sorts of different flavors, a Raspberry Pi or a bigger server on the edge. Everything is possible. The other problem deals with AI on the edge. The AI on the edge basically is a different set of problems altogether. So first, it deals with the problem of data availability. So here we have the challenge of a lack of availability and usability of raw training data for model training and inference. So you are all aware that if we have a bias of raw data from various end devices, mobile devices, if there is some lack of data. And this is a major problem in the domain of edge as well. Second problem is the question of model selection. So the state of the art requires a selection of the need to be trained AI model, and that is a challenge, right? Because sometimes we don't have the models that we have for training. Then we have the thresholds of learning accuracy and the scale of AI models for quick deployment and delivery, and the selection of these probe training frameworks, accelerator architectures under these limited resources. Because here we have the interesting effect that we nowadays have all of these accelerator architectures, but they are not standardized. So we have some edge devices which have particular NVIDIA accelerators, for example, and some others might have other accelerators. And there is no abstraction currently in place which deals with all of them. And thirdly, we have the coordination amongst those, right? So the coordination between these heterogeneous edge devices, the clouds, and everything that is between them. An orthogonal problem to all of this that I was talking about is managing the AI lifecycle itself. So what you see here is the typical AI workflow with pre-processing, training, evaluating, deploying, model creation, and the monitoring, right? So up to now, even today, most of these AI workflows are executed on the cloud alone. And what we see is, in order to be able to build really intelligent, sustainable systems, we need to decompose these different blocks that you see here and be able to distribute it onto these different parts of the infrastructure in the compute continuum. Okay? So if we do that, it has major research issues as well. And this is basically summarized in this little table here. So we can see cloud to cloud. This is C2C. We have cloud to edge. We have edge to cloud, and we have edge to edge regarding the data characteristics, the model characteristics, and which enabling technologies that we have. So you see, it's a major research undertaking here to understand how we can actually split these different AI workflows on these different parts of the infrastructure. Very few people actually, unfortunately, deal with that as of today, because most of the action is now only happening on the cloud. So to conclude this talk, I have basically three major takeaway messages. The first is that I wanted to convince you that we are now dealing with a compute continuum. This means that we have a whole infrastructure at our disposal, from the IoT to the edge to the fog and to the cloud. It's not only the cloud anymore. And if we want to build really intelligent infrastructures which are distributed and elastic and scalable, we need to look at the whole compute continuum. The second, and for that, I introduced to you a number of mechanisms that I believe are really important to achieve that. The second is that I was trying to pitch here a need for edge intelligence. This means that this is a fabric. We need to understand that this is an infrastructure which is dealing with edge that needs to bring in intelligence also to the different parts of these topologies and not only to the cloud. And thirdly, some concrete research endeavor, namely that we have AI for the edge and also AI on the edge, and both bring distinct research challenges. So I hope that I could interest you in this topic, and I'm happy for some questions and discussion. Thanks very much.
Thank you very much, Schahram. Great presentation. So I asked the participants to, if they have a question, to post it in the chat, and I take the liberty to make for a first question. Excuse me, I have a bit of cold. We're talking about the homeostasis, and you were comparing. Excuse me. You said that the homeostasis is kind of providing the equilibrium in the human body. But what about if this is damaged? Excuse me. This is really bad now.
Yes.
What would be the analog in your system if the homeostasis is damaged?
Yeah, so the analogy is, for example, if the system, it depends on your specification, right? So that's the whole purpose of these SLOs. But for example, if you have a system which is now consuming an incredible high amount of energy that you have specified that it is not allowed to do, that would be out of balance. But it can also be other criteria. So for example, certain types of resources should be used or should not be used. Anything that you define in these SLOs, that anything that utilizes these different metrics that is possible to measure and that is violated under your requirements specification is basically disrupting the homeostasis or the equilibrium of the system. I hope that clarifies a little bit.
Of course, thank you. To which extent have you also taken this kind of malfunction of the homeostasis into your kind of computation so far into account. You know that when you model this with your Markov blanket and when you do the simulation, that you also look at what about if something goes wrong, like.
Yes, yes. Yes, of course, the purpose is to, so what we do is we typically have a systems approach. So this means that we build the systems, but we also do simulations. And our goal is to find out how far can we go, basically. This is the underlying goal that we have. Of course, all the systems basically have a point where they break, right? So you cannot have endless elasticity, if you like, or endless homeostasis. But I think we can do much better than today's approach, because essentially today's systems, they can only go up to a certain level and they suddenly break, simply because of the reason that they have no causal understanding of the underlying systems that they are actually executing. So we are a little bit obsessed about causality in the last couple of years. We try to figure out how is it possible to actually connect, let's say, the software engineering part and the infrastructure part, right? Because they are completely isolated, developed by different communities. So we think that these deep SLOs are a good vehicle to actually help the developers to structure their systems and then bring in the intelligence into the infrastructure to rearrange the topology of the infrastructure so that it fulfills this requirement. Because later on, if you don't do that, no developer is able to actually say something about where things should be deployed. We need an intelligent infrastructure. Otherwise, we are really in a big trouble. Because when we really want to build a sustainable infrastructure, we need to have more intelligence in the infrastructure so that the infrastructure itself can adapt itself and not the developer, because the developer is much too late when he or she can interfere and doesn't have the information, right?
Thank you. There's a question in the chat.
Yes, IoT.
You might read it yourself.
Yes. Could it be more difficult for it to use more on the edge than on the cloud? Not sure what is actually meant here. I mean, the way that we utilize IoT in this context is IoT, as you know, can be many different things. So you can have very primitive sensors on the one hand side, but you can also have, let's say, edges with IoT and AI accelerator. So for what I mean, for example, you have AI, you have cameras which are monitoring the traffic on the street. That would be a typical IoT sensor, but it can do much more. It even has an AI accelerator. It can do computation. It can do model building, etc., on the edge device itself. So there are all sorts of hybrids in between. So IoT and edge, it's a blurry thing. And of course, one thing that is also an important and integral part of this work is also the question of resource discovery and categorization, which comes into this, because we have so many different devices. Not all edge devices are equal, which is a fundamental difference to the cloud infrastructure as we look at it, right? So typically there we have a homogeneous infrastructure, and in the edge we have a totally heterogeneous infrastructure. How much harder it is to build an infrastructure that is able to change? Yes, I guess it is much more difficult. And I don't think that many people are super amused by this approach, because of course it is bringing much more difficulty initially, because it's kind of look at the way DevOps changed the way that software engineering is working. So we look at the the infrastructure that is running the systems and the developer who is concerned with the system itself. So this is kind of a similar approach. We try to kind of bring together two different worlds, if you like. One is the world of the systems people, and the other one is the world of the infrastructure. And it's not trivial to actually convince either side that maybe a different approach is more helpful. But we believe that it is necessary to do that because for sustainability issues, we need to be able to have different levels of granularity or different levels of abstraction and be able to monitor it automatically. And this is why we think it's a good approach, a useful approach to do that. I hope that clarifies that a little bit. Yeah, so the possible ways to encode sustainability into SLO's objectives is that we have this language, a TypeScript-based language, where you are able to specify what you like. So meaning, I take this metric, I take that metric, and I specify an SLO. And that can be anything that you can measure, really, from energy consumption to CPU usage or what have you. You put them together in a formula, basically, and this is the SLO, and then we monitor them. So we do have this infrastructure to continuously monitor them in runtime, and we do have the tools now to enforce them also, meaning that we can specify elasticity strategies. This means that what do we do if these constraints that we have specified are not fulfilled? This is what an elasticity strategy is, meaning that, okay, you see that this SLO is not met. What do you do now, right? So we are able to do that. It is possible to encode that.
Since you said you can enforce it, the
elasticity strategy.
The elasticity strategy. That means you have a rule system behind to be able to order. How do you enforce it, really, when you say, I need, as I said, less energy? Yeah.
Yes. If you have specified it in the way of these SLOs, what we can do is we can then determine what is necessary in order to achieve that requirement that you have specified in that SLO. And since it is known what is the causal relationship between these different components, we are able to redeploy the system so that the necessary SLOs are met. Okay. So you take into account all these things that you have specified and redeploy things so that you can meet those requirements.
Okay. It would be interesting when you say, in your title, in sustainable internet-based ecosystems, which kind of concrete measures do you cover with this under this roof of sustainability? Is it only energy consumption, or do you have also other like water, which is then also you can say at the very end energy consumption, but is it water usage for cooling, or room usage because you need room?
We have started to do concrete use cases now. So one forthcoming paper deals with the question of videos. This is one aspect, but there are also other exactly the different types of use cases that you are mentioning. We have not focused on use cases so far regarding the applications because we first wanted to better have an understanding of the, let's say, conceptual, theoretical, and also how do we actually implement it before we go into all of these different use cases. But all of the things that you are mentioning are super valid use cases because you are able to specify things that you can measure, meaning you can specify SLOs. which then are using certain metrics, for example, for water consumption, for heating, for temperature, all of these things is possible. For example, in smart buildings, you can do that. And then you are able then to specify those as SLOs and then go on with everything that we have discussed. So all of these are possible.
There's another question I've seen.
Is AI one of the best things to help creating better intelligence? Yes, that's a very good question. So the question, as far as I interpret it, is AI better in doing these SLOs, or are human better in creating these SLOs? That's an excellent question. We have not worked on this so far because it's absolutely conceivable that after analyzing data, you can have a system proposing different SLOs to you and helping you to go from there. So far, what we have done is not this way. So far, we have done it in a manual way, basically, so that the systems engineer is developing this SLO because he or she is responsible for creating this application. But it's absolutely interesting, and we might follow this as well to look into this AI-based intelligent SLO creation way. That's a very good proposal.
So I'm looking if there are further questions. Because, yeah, if there are no further questions, I would once more like to thank you,
Thank you very much, Getty. Thank
for
you
your
very
presentation. Please, if possible, send me your slides so that we can also put them online, if it's okay for you.
I will do.
Thank you. And
thank you very much.
Thank you to the all the participants and to the interesting questions, interest in the topic in general. And yeah, as usual, I can say it's amazing how much work is ahead of us. So there's enough to do in this area. And yeah, see you next week to all the participants, and thank you once more, Schahram.
Thank you very much. Thank you, everybody. Bye-bye.
Bye-bye.